With our definition of orthogonality, we can now introduce this idea of an orthogonal complement. So what is an orthogonal complement? We are going to work with a subspace W. W is a subspace of Rn. We know what subspace means. It means that W itself is a vector space, but it's kind of a smaller portion of the larger vector space Rn. And we're going to pick element z, and z is going to be orthogonal. That's how you read that. Z is orthogonal to little w for all elements of the subspace capital W. So this vector z is orthogonal to everything inside of capital W. So we would say that z is orthogonal to w. So that's a little bit different. So far we've been talking about two vectors being orthogonal to each other. So take vector 1, take vector 2. Are they orthogonal or not? So this right here is a little bit different use of that word. We can say that z is orthogonal to a subspace or a vector space, and when we say that, we mean that z is orthogonal to every single element inside that entire subspace. So a little bit different usage, but one that kind of makes sense, I think. So let's do this. We have a single z that is orthogonal to w. Let's find all of the vectors z that are orthogonal to w. So maybe there's a z1, a z2, a z3. So grab all of these vectors. Each one of those vectors is orthogonal to every single element of the subspace W. That entire set of vectors we call the orthogonal complement of W. So the orthogonal complement of a subspace is another collection of vectors, and it has the property that every single thing in the orthogonal complement is orthogonal to every single thing in W. We use this notation. We use W kind of raised to that orthogonality symbol. So this itself is a set. We call it the orthogonal complement of W. And it has this property right here. Anything that I pick from the orthogonal complement is orthogonal to everything in W, right? So every vector z is in this if z is orthogonal to all the elements of our starting subspace. Okay. So let's kind of go through a nice result for orthogonal complements. One way to see if an element is in the orthogonal complement is kind of to loop over every single element of the subspace and perform the check, right? Is z orthogonal to w? And then keep picking the little w's over and over and over and exhaust every single element for all the little w's in the subspace W. There's kind of an easier way to do that check though. And the easier way to do that check is if we know if W is the span of some bases. So let's say that W is the span of our bases, vectors v1, v2, all the way up to vr. And let's go ahead and assume that x is orthogonal to all of these v's. So x is orthogonal to v1, orthogonal to v2, etc. And then let's just pick some arbitrary element from our subspace capital W. Well, since little w is an element of the subspace capital W, that means that we can write it as a linear combination of the basis, right? That's exactly what it means to be in this set. It means that you have to be some linear combination of the v's. So no matter what I choose for little w, I can write it as a linear combination of v's. Let's go ahead and compute now what the dot product is between x and w. So let's compute x dot w. So that's going to be x dot this, because that's what w is equal to. Then I can use the distributive property of my dot product, pull the scalars out front, and I just end up with alpha 1 x dot v1 plus alpha 2 x dot v2 all the way down. But we know something about x. We know that x is orthogonal to all these v's. So each one of these dot products right here is actually equal to 0. So I end up with just alpha 1, 0 plus alpha 2, 0 all the way down alpha r plus 0, and I get 0. So let's think about that. We just figured out that x dotted with this basically arbitrary element from the subspace W was orthogonal to it. So that means that x must be in the orthogonal complement of the subspace W, just by direct computation here, right? So x is in the orthogonal complement, and note, Really what we had to do here is we only had to check to see if x was orthogonal to each basis vector of the subspace. So I didn't have to loop over every single element of the subspace W. All I have to do is check to see is the vector I selected orthogonal to each basis vector. And in general, that basis vector, there could be just 2 of them or 3 of them or 4 of them, whereas there's definitely an infinite number of things in the subspace W. So checking for if a certain vector is in the orthogonal complement or not, I think the easiest way to do it is just go check and see if that vector is orthogonal to each of the basis vectors of the starting subspace. And if it is, then we land in the orthogonal complement. So that's just kind of a nice result to note. So that's it for now. We have talked about what we mean by the orthogonal complement of a subspace.